All right. Hi, everyone, and welcome to the Reinforcement Learning Theory seminars. Today, it's our pleasure to have Noah Golowich. He is a last year PhD student at MIT, working on various topics in online learning, game theory, multi-agent learning, and reinforcement learning theory. And today, he is going to talk about exploring and learning in sparse linear MDPs. Welcome, and Noah, the stage is yours.
Great, thanks for the introduction, and thanks for inviting me to speak here. So I'm going to be talking about joint work with Ankur Moitra and Dhruv Rohatgi on sparse linear MDPs. Okay, so I'll begin by giving some background on linear MDPs and sparse linear MDPs, as well as the main question that we're considering. Then I'll discuss our main results, an application to learning block MDPs, and finally I'll discuss some overview of the proof. So probably most of you know this, but reinforcement learning describes the problem of a learning agent interacting with a changing environment over a series of episodes. The goal in reinforcement learning is for the agent to explore its environment and thereby learn enough about it so as to find a good policy, namely one which maximizes some measure of reward. So RL has numerous applications ranging from game playing to robotics and healthcare. It's also been used, similar ideas from RL have been used in training large language models, and there's many exciting applications of RL. And typically, the reinforcement learning problem is formalized through the model of Markov decision processes. So I'll briefly review the notation for MDPs. An MDP, or Markov decision process, consists of the following components. There's a horizon H, which is a natural number, an action set capital A, and a state set capital S. There's an initial state distribution D over states, a transition kernel P of S prime given SA, which gives the probability of transitioning to S prime, given that we're in state S and take action A. And finally, there's a reward function R of SA, which tells us the reward that the agent receives if we're in state S and take action A. So a trajectory in an MDP consists of a total of capital H steps. At the first step, the initial state S1 is drawn from the initial state distribution D, and at each step, little h thereafter. The agent observes its state SH, and then it chooses an action AH according to some policy. As a function of SH and AH, the agent receives reward R of SH AH, and then it transitions to a new state SH plus 1 according to the transition kernel P. Now, as I said, an agent chooses actions according to policy. Formally speaking, a policy is a tuple pi consisting of mappings pi 1 through pi capital H, where each pi little h is a mapping from states to distributions over actions. And we let capital pi denote the set of all policies. The value of a policy, or v pi, is simply the expected value over a trajectory drawn from the policy pi of the sum of rewards from step 1 to step capital H. So that's shown here. And finally, the optimal policy pi star is a value maximizing policy where the maximization is over all policies. Okay, now the goal in reinforcement learning that we're going to be considering is to find a policy pi hat which has near optimal value. Namely, we want v pi star minus v pi hat to be small. And the way we do this is to consider the online RL setting. So the agent is going to interact with the MDP in a series of episodes. In each episode, the agent chooses a policy pi t, it executes it, and it observes a trajectory consisting of states, actions, and rewards drawn from the policy. It then uses this data to choose another policy pi t plus 1, and it repeats this procedure for a total of capital T episodes, after which the agent outputs some candidate policy pi hat, whose value should be near optimal. Now we measure the sample complexity of this procedure by the number of episodes T of interaction. So I'll refer to the number of episodes as the number of samples. Now, in the setting when the state and action spaces are small, then it's well known that there are efficient algorithms, both in a statistical as well as a computational sense, for finding a near optimal policy. In particular, the statistical cost and also the computational cost scale polynomially in the number of states and actions. But in many of the applications of reinforcement learning, which I mentioned earlier, the state space is often extremely large, and so these guarantees don't really give us anything interesting. In light of this observation, it's natural to come up with classes of MDPs which admit large or infinite state spaces, but nevertheless have sample-efficient algorithms. And in recent years, there's been a great number of examples of classes of MDPs which meet these two requirements. So these include block MDPs, low-rank MDPs, linear MDPs, MDPs of bounded Bellman rank, and many other examples. And there's been a great deal of successful work which gives a pretty good characterization of the sample complexity of learning MDPs with large state spaces. One issue with many of these results is that for many of these models, the existing algorithms completely ignore the computational aspect of the problem. And even when computation is considered, many of these algorithms require oracles that solve subproblems which are often intractable. And in light of this, this shortcoming, it's natural to add a third requirement to our list of desideratum, which is that there be end-to-end computationally efficient algorithms for learning a near-optimal policy in these MDP classes. In particular, we don't want any reliance on unimplementable oracles. And when you add this third requirement, most of these existing examples no longer satisfy it. In particular, the only one that does is linear MDPs, which will be the subject of this talk. I want to emphasize that requiring end-to-end computational efficiency gives us a window into reasoning about which algorithmic ideas are likely to be efficient in practice. And in particular, it could suggest structures of the MDP, or at least heuristics, which may lead to faster algorithms. Okay, so now I'm going to discuss linear MDPs. So an MDP is a linear MDP if the following holds. There must be feature mappings phi, mapping from the state and actions to d-dimensional Euclidean space, as well as a mapping U from the state space to d-dimensional Euclidean space. So first of all, for all tuples SA S prime, the probability of transitioning to S prime from SA is the inner product between phi of SA and mu of S prime. We also require that for all SA, the reward that we receive at state action pair SA is the inner product between phi of SA and some fixed coefficient vector theta. So in words, the requirement of being a linear MDP is simply that the transitions and rewards be linear in the feature vectors phi. Alternatively, you can think of it as saying that the transition matrix is low rank, in particular, its rank is D, and most D. Now, it's pretty typical in the study of linear MDPs to assume that the features mu are unknown. In other words, these must be somehow learned by the algorithm, but that the feature mappings phi are known. And under this assumption, a seminal work by Jin Young, Wang, and Jordan showed that there is a computationally efficient algorithm for learning a near-optimal policy in linear MDPs. In particular, the computational cost and sample costs scales polynomial in the dimension D and the horizon capital H. But this result overlooks one crucial question, which is where do the features phi come from? The features phi of SA must somehow capture the relevant information about a state action pair for determining its transition to the next state. And given some reinforcement learning problem, which we don't a priori know much about, it's not at all clear what features are actually useful in capturing the transition information. Okay, so how can we find these feature mappings phi? One potentially naive approach for doing this is as follows. Let's let phi of SA denote some concatenation of all possible features phi I, where phi I are mappings from state actions to real numbers. So for instance, some of the phi I could be neurons from some intermediate layer of a pre-trained neural network, which we might expect captures some of the relevant dynamical information about the state action pair. Other possibilities, which are a little bit more old school in nature, would be to use heuristics based on domain knowledge to choose some other features VI. Now, the key assumption that we're going to make is that out of this large number D of features, only a small number K of them are actually useful in specifying the transitions. And this assumption leads us to the definition of a sparse linear MDP. So for some parameter K, we say that a K-sparse linear MDP is a linear MDP for which there's some unknown subset J of features of size K, so that for all states S, the feature vector mu of S is supported on J, and also the coefficient vector theta is also supported on J. So to understand what this means, it's useful to go look at the definition of a linear MDP. The constraint that the coefficient vector, the feature vector mu of S prime be supported on the subset J means that the only features in the feature vector phi of SA which matter in determining the transition are those supported on the set J. And similarly, for the reward vector, the only features which matter are those indexed by the set J. And so this definition is exactly capturing, our kind of intuition that a small number of features should be useful in determining the transitions. So in the definition of a sparse linear MDP, there's additionally some technical norm constraints that we need. We need the L infinity norm of all feature vectors to be at most 1. And we also require a bound on the sum of the L infinity norms of the feature vectors mu of S prime. And these are relatively standard conditions. Now here's the main question pertaining to learning sparse linear MDPs. Suppose we're only given a number of episodes of interaction, which scales as a polynomial in the sparsity as well as log of the dimension, then can we efficiently learn a near optimal policy? Now, the main point to distinguish between this question and the previous result for learning linear MDPs is that we no longer have sample complexity that can scale polynomial in D. The number of episodes of interaction must only be polynomial in K, which is much less than D. And I'll note that we also want the dependence on the other parameters, namely the number of actions and the horizon, to be polynomial. Okay. Oh, is there a question?
Yeah, it's me. So you had this assumption about mu, that the sum of the L infinity norms of mu S prime over S prime is polynomial in K, and you say that this is a standard assumption. Convince me that this is the case. So for example, yeah, like, is it true that like if we replace K by D, then this was an assumption that was used? It's like, how is this working? Like the mu S prime, it's a D-dimensional vector. The maximum component of that, like summed over all possible states, like that's a, yeah. That seems like very stringent to me, and I don't remember this assumption in the original linear MDP works.
Yeah, so the original linear MDP work does not explicitly make this. They have the norm outside the sum, but there's actually there's a slight error in one of the proofs, and you actually need the norm inside the sum for it to go through.
Seriously?
Yeah, so at least in that paper, like you need the norm, in the way that we wrote it here, where it's inside the sum. Statistically, you can make do without this constraint. But for that original linear MDP paper, you need like this constraint to be poly D.
Okay, that's a bummer. I will go back to the proof and see what's happening there. Okay, yeah, thanks for pointing that out. Yeah, and you say that there is a fix for the original work that would make the proof go through with the norm outside of the sum. Is that true?
So okay, if you want the norm outside the sum, definitely like something like Olive would work. That's not going to be computationally efficient.
It's not going to be so the price of that is computation.
Right.
That's That's super surprising. We had a recent paper that was doing some other, like, was following some other type of algorithm, like NPG style. I don't think we have this part of the proof works quite differently from the original. I don't think that we need to have the L infinity norm inside. That seems to be, that's also computationally efficient. It worsens rates a little bit, blah, blah, blah. Some parts of improve, some parts of got worsen. That's interesting. That's very interesting. So you say that there is an open problem there. Is that right?
So okay, I guess the one final thing I was going to state is there actually some of these recent, there's some recent work like Vocal by Ujia and others, VOQ, I don't know how to pronounce it, VOQL. This algorithm is the optimal sample complexity for learning in linear MDPs computationally efficiently. They appear to have this norm inside the sum, although I haven't kind of made sure that they're avoiding the same issues in the initial linear MDP papers. So I haven't looked at that carefully.
Okay. So some homework for us. Okay, it may or may not be an open problem. Who knows? Okay, got it.
Yes.
That's really interesting. Thanks.
Yeah.
Wow.
But yeah.
Also, yeah. Okay. So as far as I remember, like there was a 2 norm and like square root decoming and like slightly different assumptions than what you're saying here.
Yes. So I guess the linear MDP paper would have like a 2 norm and a root D bound.
Yeah.
We're kind of ignoring poly factors. So if you just think of, K is playing the role of D there, then it's equivalent up to a poly K factor.
Got it. Okay. Good.
Cool. Any more questions? Okay. So now I'm going to discuss our main result, which gives an affirmative answer to the main question. What we show is that there's an algorithm that takes a number of episodes of interaction, which is a polynomial in K and log D, with this K-sparse linear MDP, and it outputs an epsilon optimal policy with high probability. The running time is a polynomial in D, as well as the other parameters. Okay, now let me give a few remarks. The best prior result for the sample complexity, namely one which scales a polynomial in K and log D, is to have computational cost roughly D to the K. So it's exponentially worse than our algorithm in the sparsity K. And this is achieved by any number of recent algorithms which uses the principle of global optimism. For instance, Olive achieves this guarantee.
But okay, so sorry. So here you're saying that the obvious bound for Olive would scale is D to the K, and are you claiming a lower bound as well, that for global optimism you will need to have this, or this is just saying that like the naive bound would give this?
Yeah, this is just a naive bound. I'm not claiming a lower bound.
Okay.
I would suspect that a lower bound probably holds.
Could there be? Yeah.
There's some result that shows that in the worst case, like Olive can be hard to implement. And
it's like what paper is that? I try to hunt it down, but I keep failing.
It's a paper by, I think, Chris Dan and some others. I don't know the title off the top of my head, but I can.
Okay. Find it. Yeah, that would be good.
Okay. Yeah, I'll send that.
Nice. Thanks.
Yeah. I'll also note that the polynomial dependence of our sample complexity on the number of actions in the horizon is necessary, as has been shown in some prior work. Now, one way to think of our algorithm is that it's an analog of the guarantee of the lasso algorithm for the prediction task in sparse linear regression. And I'll say more about this later in the talk. The lasso algorithm also guarantees sample complexity, which is polynomial in the sparsity and log dimension, and running time, which is polynomial in the dimension. Now, while it's an analog in this sense, the proof of the theorem is kind of entirely different. And one of the reasons that it has to be different is that we're not making any restricted eigenvalue assumption. There's been some previous work on sparse reinforcement learning, which does require a sparse restricted eigenvalue condition. And in some sense, making such an assumption kind of eliminates the need for active exploration, because the restricted eigenvalue assumption essentially requires that the feature vectors span a well-conditioned, or in some sense exploratory, distribution. And in fact, making do without such an assumption leads to some of the main technical obstacles that we have to overcome in our proof. Moreover, once again, kind of expanding this analog with the lasso algorithm's guarantee for sparse linear regression, our theorem also holds under a more general analytical notion of sparsity, namely one of bounded L1 norm, which I'll discuss in a few moments. Okay, now before discussing the proof of our theorem, I'm going to talk about an application, which is to learning in block MDPs. So the motivation behind reinforcement learning for block MDPs is to do RL environments with rich observations but simple dynamics. So imagine, consider, for instance, the task of a robot which has to move a table from one side of the room to the other side of the room. On the one hand, the underlying physical dynamics of this problem are very simple. We have solid objects, and the physics of this problem are really not that complicated. But the robot's sensory input might be much more complicated. Supposing that it receives its input from cameras, it sees not only the table that it wants to move, but the entire background of the room and the outside. There's also a TV in the room. Someone might turn that TV on and start flipping between channels. All of these exogenous information kind of is in a statistical sense very complex, and you really can't hope to efficiently learn everything about that room. But all we need to really understand is the simple dynamics. We have to find some way of filtering out all of this exogenous information. And to model this type of challenge, people have used the notion of block Markov decision processes, or block MDPs. Block MDP is similar to an MDP in that it has a horizon capital H, an action set A, and an observed state set S. But there's also an unobserved latent state set Z. And this forms the main difference with MDPs. So on the latent state space, a block MDP has an arbitrary MDP structure. And this is specified by some transitions kernel tilde-p, as well as some rewards tilde-r. Now, we don't actually observe the latent states directly. Instead, we observe states from the observed state space S, which are drawn according to some emission distribution Q of S given Z, which gives the probability of seeing state S, given that we're in some latent state Z. Now, the key assumption that makes a block MDP tractable, both in a planning sense as well as in a learning sense, is the existence of a decoding function, rho star, mapping from observed states to latent states, which satisfies the property that it always correctly decodes an observed state. So in particular, with probability 1, for S drawn from the distribution of Q of Z, rho of S always decodes Z. And now the transitions and rewards of a block MDP factor through the decoding function rho star. So you can kind of think of this pictorially as is shown here. We have two layers, basically an unobserved MDP in a latent state space, and then observed states, which are drawn independently at each step, given the latent state. Now, it's typically assumed that the size of the latent state space is small, but that the observed state space is large. So we're okay with sample and computational costs, which are polynomial in the size of Z, but not in the size of S. In order to make block MDP statistically tractable, it's necessary to make the following assumption, namely that there be a known class of decoders phi, mapping from the observed states to latent states, which contains the true decoding function rho star. A great deal of existing work, some of which is shown here, shows the following. If we're given an oracle for the class phi, then we can solve the block MDP problem, namely learn a near optimal policy, with sample complexity scaling as a polynomial in the size of the latent state space, as well as log of the size of phi and the other parameters. Now, there's one key catch here, which is that for essentially any known class phi, the oracles of these papers that I've mentioned are often not implementable in a computationally efficient manner. And the reasons for this are numerous. One issue that comes up a lot is that these oracles need to handle noise. We only have efficient algorithms for noiseless versions of the problem. In many cases, learning with noise runs into barriers relating to the hardness of agnostic learning. Another problem is that many of these oracles require the learning to be proper, namely that it outputs some decoder in the class phi, whereas in many settings in supervised learning, we only have computationally efficient algorithms which are improper learners as opposed to proper learners. And there's several other reasons for which these oracles are not efficient. So in light of these challenges, the following is a very natural question. What is some reasonable structure for phi, some concrete class of decoders, which enables computational efficiency for the end-to-end learning of block MDPs? And as a corollary of our main result, we're able to answer this question, namely we're able to give some concrete class of block MDPs which are learnable. And this class of block MDPs is what we call decision tree block MDPs, which is the set of block MDPs for which the class of decoders is the class of decision trees. So formally speaking, the state space, the observed state space, is the set of all length n binary vectors. And the latent state space Z is a set of integers from 1 to k. You should think of k as, say, a small polynomial in n. Now, the class phi is given by the set of depth log k decision trees whose leaves are labeled by elements of the latent state space. So let me remind you of what this means. The input to the decision tree is some observed state S. Now, the decision tree at each node, it looks at one coordinate of S. And then, depending on whether that S at that coordinate is 0 or 1, it takes either the left or the right child. It does this for a total of log k steps corresponding to the depth of the tree. And finally, it outputs the label of the leaf, which is simply a latent state, namely an integer from 1 to k. Okay, so what our main theorem says is that we can efficiently learn the class of block MDPs. The sample complexity is a polynomial in the number of latent states k, as well as log n. And the number of episodes of interaction is n to the log k. So it's not quite polynomial in k and n, it's quasi-polynomial. Now, the way we prove this is that as an immediate corollary of our main theorem, by observing that these decision tree block MDPs with parameters n and k are actually Ka sparse linear MDPs in a number of dimensions d, which scales as n to the log k. And this n to the log k scaling of d is exactly why our algorithm takes quasi-polynomial running time as opposed to polynomial running time. I'll note that the previous best running time for getting poly k sample complexity for decision tree block MDPs was n to the k, which is once again achieved by Olive. So we get basically, a nearly exponential improvement on the prior running time. Okay, so in the remainder of this talk, I'll discuss some ideas behind the proof of our main theorem. Before doing so, I'm going to discuss a generalization which I mentioned earlier, namely a guarantee for analytically sparse MDP learning. So an analytically sparse MDP is one where the feature vectors have an L1 norm bound as opposed to an L0 norm bound, which is the sparsity. So it's a convex relaxation of sparsity. And formally speaking, we say an L1 norm-bounded linear MDP with norm-bound k is a linear MDP for which the following constraints hold. Once again, we have an L infinity norm constraint on all phi of SA. But now we require that the sum over all states of the L1 norm of mu of S prime is at most k, and also the coefficient vector theta of L1 norm at most k. Now, it's straightforward to see that a k-sparse linear MDP, as I defined it earlier, is an L1 norm-bounded linear MDP with norm bound, which is a polynomial in k. And this follows as a result of the sparsity constraint, as well as the fact that we assume the L infinity norm of all mu of S prime sums to at most constant or k, or rather a polynomial in k. And the L1 norm of a k-sparse vector is at most k times its L infinity norm. Okay, so what our main theorem actually can be generalized to the setting of L1 norm-bounded linear MDPs, namely with the number of episodes of interaction that scales as a polynomial in the norm-bound k and log d. We can find a near-optimal policy with running time, which is a polynomial in d. Okay, now to understand how to prove this theorem, one more preliminary we'll need is some background on sparse linear regression. The setup of sparse linear regression is the following. We're given samples xy drawn from some distribution d, where x is a vector and y is a scalar whose value is equal to the inner product of x and w star plus zero mean noise eta. Now w star, the coefficient vector, is assumed to have L1 norm at most k, which is generally speaking much less than the number of dimensions d of the vector x. And a fundamental result shown by Tibshirani and later extended in many ways establishes the following. With high probability over a data set of size n drawn from the distribution d, the solution w hat to this convex program has low mean squared error. In particular, the expected value for a feature vector x drawn from d of the square of the inner product of x and w hat minus w star is at most epsilon, as long as the number of samples n is at least a polynomial in k log d and 1 over epsilon. Now this estimator w hat, which simply is a minimizer of the mean squared error on the data set, constrained to have L1 norm at most k, is known as the lasso estimator. And this result, this lasso estimator, is in the canon of statistics. It's an extremely influential and important result, which has been used for numerous applications over the past several decades. And in light of this, really great influence of the lasso, one question is, well, does using the lasso simply suffice for sparse reinforcement learning? Now, the answer to that question is that while it's absolutely necessary, we'll use the lasso, it is by no means sufficient, and in fact, many new ideas are required to solve sparse RL. At a high level, the reason for this is the following, which is that in reinforcement learning, the distribution D over covariate vectors and labels is not fixed, but rather it depends on the policy, which induces a distribution over feature vectors at each state, which can obviously change depending on what the policy is. And one of the main challenges that we'll face is that we don't assume a restricted eigenvalue or any sort of well-conditionedness assumptions under any policies. And so we cannot hope to perform parameter estimation. Namely, if W star, say, index is a coefficient vector for the rewards at some step, we cannot hope to learn this vector W star in any sort of norm, like the L1 norm. And this is problematic for the following reason. In reinforcement learning, certain directions of W may not be learnable under one context distribution, but it may nevertheless be necessary to learn them in order to with respect to a different distribution. So let me give an example here. Suppose that there's some policy which produces feature vectors which have a small vertical component. In particular, suppose that the feature vectors are drawn from some distribution which, roughly speaking, forms this green point cloud in 2 dimensions. Now, obviously, we cannot hope to learn the coefficient of reward vector W star in the vertical direction if we only see samples from this green distribution. But it might be the case that the optimal policy induces a distribution over feature vectors, which is given by some other distribution, I'll call it D2, which is a large vertical component. So in order to figure out what action to take at this step, under the optimal policy, we need to learn the direction of the rewards, W star, in this vertical direction. And so the conclusion here is that in some sense, we have to explore all possible directions which are attainable under some distribution over features induced by a policy. And in a formal sense, the way we do this is by learning a policy cover, which is a set of policies which visits each state with near maximum probability. So at a high level, the way our proof goes is, first of all, to show that there exists a small policy cover using a variant of the greedy algorithm. Now, this greedy algorithm assumes knowledge of the transitions, and therefore, in the second step of the proof, we're going to remove this knowledge of transitions by constructing a set of estimated transitions, which satisfy certain properties. We call this set of estimated transitions an emulator, and this is one of the main technical contributions of our proof. Okay, so this is roughly the outline, and now I'm going to go into more detail on each of these steps. First of all, let me formally define a policy cover. To do so, we'll need the following definition. For state S in step H in policy pi, I'll let dH pi of S denote the probability that the hth state on a trajectory drawn from pi is equal to S. Now, for some parameter alpha between 0 and 1, an alpha approximate policy cover at step H is a set psi of policies, so that for each state S, the probability that a uniformly random policy drawn from the cover of psi visits S at step H is at least an alpha fraction of the maximum possible probability. And these visitation probabilities are exactly these measures dH pi. Now, why is learning a policy cover useful? It essentially boils down to the following fact, which is that there's an efficient algorithm known as the policy search by dynamic programming, or PSDP algorithm, which satisfies the following guarantee. It takes as input an alpha approximate policy cover at each step little h. So we have policy covers psi 1 through psi h. Then for some positive integer n, the algorithm PSDP samples n trajectories from m using these policy covers, and then it outputs a policy pi hat whose suboptimality is bounded by a polynomial in the various parameters, namely HA sparse decay and 1 over alpha, times an inverse polynomial in the number of samples n. Now, this is a relatively standard algorithm, and I'm not going to say too much about it, but roughly speaking, the way it works is by using a dynamic programming-like procedure to estimate the output policy pi hat at each step little h, going from capital H all the way down to 1. So it's a backwards inductive-like procedure. And at each step, given our knowledge of the policy pi hat at later steps, we can estimate the value function, which is going to be a linear function, at step little h, using the lasso algorithm. This also uses, of course, the L1 norm-bounded assumption on the linear MDP. And then once we've estimated this value function, we can simply define pi hat h at each successive step h to be the greedy policy with respect to that value function. Okay, so what this guarantee means is that once we found a policy cover, we're good. And so the bulk of our proof is to construct a policy cover. The way we do this is to use a stepwise procedure. And in fact, now we're going to go in order of increasing steps. So we're going to first construct a policy cover of psi 1 at step 1, then psi 2 at step 2, and so on. How do we do this? Well, at each step little h, using the cover psi h minus 1, we somehow want to explore as many directions as possible. Now, one challenge here is that in RD, there's a total of d different directions, or d orthogonal directions. And we can't explore all of these d different directions because we only have poly k log d samples. So we can't use separate trajectories to explore each of these different directions. And in particular, what this means is that some sorts of natural approaches, which have been used for many similar problems for exploration RL, such as the use of a barycentric spanner, won't suffice here, because these approaches typically all require a number of samples that scales as polynomial in the ambient dimension D. And so to perform the exploration task, we actually need to use some new ideas. And to discuss these ideas, it's useful to actually take a step back and to consider the existential question. namely whether a policy cover that we desire actually exists. Now, one of the obstacles or one of the challenges in showing that this thing exists is the requirement that the approximation parameter alpha scales a polynomial in 1 over the sparsity. The reason we require this is that the sample complexity of PSDP scales as 1 over alpha. So if we want the number of samples to be polynomial with sparsity, alpha had better be a polynomial in 1 over the sparsity. So how can we show that such a policy cover exists? We're going to do so using a greedy approach. It takes as input a step h, at which we want to construct the policy cover as well as some parameter c. And what this greedy approach does is it initializes psi, the policy cover, to be the empty set, and then it initializes b to denote the set of all states. And we'll maintain the invariant that b will always contain uncovered states. So we'll repeat the following procedure. We're going to define a residual vector mu res, which is a sum of feature vectors mu of s over all uncovered states in the set B. Then we're going to choose a policy pi bar, which maximizes the following quantity. So in symbols, it's the expected value of a feature vector at step h, the residual vector. But really what this is doing, by using the definition of linear MDP, is maximizing the total probability with which we visit a state in the uncovered set of states. So this is kind of a natural thing to do. We're just choosing a policy to maximize the total uncovered mass so far. Now, if the total uncovered mass is small, if it's less than this cutoff c, then we're going to break. At this point, we've covered most of the state space, and we're going to kind of ignore the rest. If this break condition does not hold, then we're going to add the maximizing policy pi bar to the cover of psi, and then we're going to proceed. To do so, we have to, of course, remove states from the set B, which are covered by the policy pi bar. And these are namely states whose visitation probability at step h plus 1 is sufficiently large as compared to the L1 norm of mu of s. And finally, at the end of this procedure, we're going to return the cover of psi. So basically what's going on here is we're using the L1 norm of the mu of s vectors as a sort of potential function to characterize how much of the massive states we're covering. And the fact that this procedure terminates is a consequence of the boundedness of the L1 norm, of the sum of the L1 norms of the feature vectors mu of s. And so in particular, at each step where we don't terminate, we cover a set of states in proportion to the sum of the L1 norms of these set of states. The boundedness of the L1 norms makes sure that this will not go on forever. Okay, so what we can show is that this procedure greedy cover finds an alpha approximate policy cover at step h plus 2, where the parameter alpha scales the polynomial in 1 over k in one of the number of actions. Now you'll notice that there's a little bit of an inconsistency here, that this says step h plus 2. It turns out that this is due to some technical issues which arise as a result of the fact that we're only there's some error probability in greedy cover. We have to take a uniformly random action at step h plus 1 to deal with this error probability, but that's not actually that important for the purposes of this talk. What is important is that there's a few key obstacles to implementing greedy cover in an efficient way. One obvious obstacle is that greedy cover requires knowledge of the feature vectors mu of s. For instance, to compute the residual vector at each step. A second obstacle is that even if we knew the feature vectors mu of s, it takes amount of time, which is polynomial in the number of states, to implement greedy cover, because we have to iterate through all the states. So how do we overcome these obstacles? Well, what we're going to do is we're going to try to estimate a small representative states that well approximates the transitions in some sense. And if we can do so, then when we implement greedy cover, we can simply use this small representative states, as well as some estimates of the feature vectors mu at those states, as a replacement for the set of all feature vectors mu of s in the execution of greedy cover. And this idea of approximating the state set by some small representative states leads us to the notion of an emulator. So, at a high level, kind of putting things in context, an emulator is an example of a common algorithmic paradigm that when you're faced with a complex structure, you want to find some simpler, smaller structure, which well approximates it. In this case, the complex structure is that we don't know the feature vectors mu of s, and there's too many s. And the solution given by an emulator is to replace the set of all mu of s, ranging over all states s, with a small set of approximate feature vectors, which we'll call mu hat j, where j ranges from 1 to some relatively small parameter m. Now, the takeaway here is that this gives a model-based approach, in some sense, for linear reinforcement learning. Many of the prior approaches for linear RL, in fact, most of them, are model-free in nature. And this is essentially because of the non-parametric nature of linear MDPs. There's infinitely many parameters, namely the d parameters of each feature vector mu of s, indexed by all states s. And of course, the number of states may be exponentially larger or infinite. And what we're doing here is we're essentially kind of approximating this model, the set of all mu of s, by some smaller set. And that's why I call this kind of a model-based procedure. Okay, so what is the right notion of approximating the transitions with diffuse states? To understand this, it's useful to take a look at the key step in the analysis of greedy cover, which guarantees that for all states s and policies pi, the average state visitation distribution at state s for a uniformly random policy from psi is at least a factor of alpha times the state visitation of state s under policy pi. Now, I've written out the kind of expansions of these visitation probabilities in terms of the feature vectors at step h plus 1. And what we want to do is we want to take the set of feature vectors mu at step h plus 1 and replace these with some approximation of them, so that when we exchange the true feature vectors with their approximations, the expected feature vector at step h plus 1 does not change much. In other words, we want to preserve the expected feature vector at step h plus 1 under any policy pi. So let's write down what this means. We want the expected feature vector under policy pi at step h plus 1 to be close to its approximation L infinity norm. And the reason for the L infinity norm is simply because it's dual to the L1 norm. Now, what do each of these terms look like? Well, the expected feature vector under pi is simply the sum over all states of the probability of visiting the state s at step h plus 1, which is the first term in this sum, times the value phi at state s with respect to the policy pi at step h plus 1. Now, what does the approximation look like? Well, the way we get this approximation is we choose vectors mu hat 1 through mu hat m in d-dimensional Euclidean space, together with corresponding states s hat 1 through s hat m. And then this approximate feature vector is the following. We're summing over all j. Instead of summing over all s, we replace the mu of s with mu hat j, and replace the states s with s hat j. And so we want the difference between these two quantities to be at most epsilon. Now, given such a set of feature vectors mu hat j, as I mentioned previously, we can just run greedy cover where we replace the set of all mu of s with the set of all mu hat j. Now, there's a minor issue, which is that while we would be good if we could satisfy this constraint in the yellow box, it actually seems a little bit too strong for our needs. In particular, it seems hard to estimate the feature vectors mu hat j so that this thing holds. And the reason for the hardness is actually not that deep. It's just that at step h plus 1, the policy might be arbitrary, and this leads to some kind of technical difficulties in ensuring that this constraint holds. And so the way we get around this minor issue is simply by assuming that the arbitrary policy pi, in fact, takes a uniformly random action at step h plus 1. And so accordingly, we'll define the average feature vector at a state s to be the 1 over a times the sum over all actions a of phi of sa. And when we do this, we arrive at the definition of an emulator. So an emulator at step H is a set of vectors mu hat 1 through mu hat m. So there exist states s hat 1 through s hat m, for which, as I kind of wrote in the previous slide, the vectors mu hat j and s hat j induce transitions which approximate the expected feature vector at step h plus 1 under any policy pi which takes a uniformly random action at that step. Now, in math and symbols, this is what it looks like. This is essentially the same constraint as from the previous slide, where I now have an average feature vector at step h plus 1. There's some additional conditions which we need for technical reasons. First of all, the mu hat j must be analytically sparse. And in particular, the sum of their L1 norms be bounded. And moreover, the mu hat j must induce non-negative inner products with the expected feature vector under any policy. That condition looks like this. And this condition is somewhat natural because the value on the left-hand side of this inequality, namely the inner product between phi of shah and mu hat j, in some sense should represent some sort of probability, namely of reaching some imaginary state indexed by mu hat j at step h plus 1. And so, of course, we want that to be non-negative. Okay, so the last remaining piece is how do we actually find such a set of feature vectors mu hat j? And the way we'll do this is to solve a convex program. So in particular, the procedure for doing this, which we call estimate emulator, takes as input as step h, a policy cover psi at step h, and parameters epsilon n and m. It then draws data sets consisting of state action pairs at step h and also states at step h plus 1, using a uniform policy in the policy cover psi. And then it will solve a convex program in the variables mu hat 1 through mu hat m using these data sets. And roughly speaking, what the constraints of the convex program say is that the emulator conditions must hold with respect to these variables mu hat j, and will ensure that they hold for any policy in the for any policy pi, by roughly speaking ensuring that they hold with respect to the feature vectors of these data sets at step h and step h plus 1. And we'll use the coverage policy of the coverage property of policies in psi to ensure that this actually guarantees the emulator conditions in the previous slide hold. In the interest of time, I'm not going to go through the details of this convex program. It's somewhat technical, and it would take a while to explain. But I'll just state that what we can show is that a feasible solution to this convex program, first of all, exists, and it will be an emulator at step h with high probability. Okay, so let me now kind of put all these pieces together. The way our overall algorithm works is at each step little h, we're going to call estimate emulator to compute an emulator at step h using a policy cover at prior steps. Then we'll pass that emulator to the greedy cover algorithm, which will then give us a policy cover at step h plus 2. And we can then repeat this procedure in order of increasing h. Finally, we'll call PSDP to compute the optimal policy given a policy cover, which was produced by this greedy cover procedure. And that's it. Then that'll give us an optimal policy. So to conclude, I'll just say that we give the first computationally efficient algorithm for learning a near optimal policy in sparse linear MDPs. This also has applications to the end-to-end learning of block MDPs. There's a bunch of open questions, such as improving the sample complexity, coming up with other models for end-to-end learning of block MDPs, and also finding other applications of emulators. Thank you for listening.
All right, thank you. All right, we have time for questions. Maybe I can start. I was also curious about this assumption that Java pointed out, like the sum over the norms being less than k. Can you maybe explain how this is used in the proof? Or why do you need this? Or even the prior work needs it, as you said.
Yeah. So like the place where the prior work needs it is if you want to prove that any value function, so just in a linear MDP,
Mhm.
you want to prove that any, say, bounded function at step h+1, mapping from states to reals, has a Bellman backup, which is a linear function whose coefficient vector is bounded in L2 norm, you're going to need to use this assumption. So particularly if you want boundedness of the value functions, or at least the boundedness of the coefficient vectors for the value functions, the only way I know of showing this is to use boundedness of the sum of the of the norms.
Mm-hmm.
Is this where you are also using this or no? Like you were using it in a much stronger way in constructing the emulator as well, right? Like the emulator simply wouldn't go through if you try to relax this to the one that appeared in the original work.
Yes. So we obviously need it in the sense of the original work to ensure the coefficient vectors are bounded, but you're right that we also need it for the construction of an emulator. Yeah, I guess like that's correct that we are using it in a stronger way. And I don't know how to extend our algorithm, or if we didn't have such a norm bound.
Right.
This actually kind of relates to this this notion of kind of online learning, online RL under these coverage properties. There's a paper by Dylan Foster, Tungyan Xie, and several other authors, which show that if you have kind of MDP with kind of a bounded coverage parameter, which is typically used to ensure that offline RL is sufficient, and then you can actually do online learning of RL. And the kind of property that we get of the MDP from having this norm-bound assumption is essentially exactly this coverage property. So really, it's that coverage property which is the main thing that our greedy cover algorithm needs.
So the block MDP construction is very interesting and nice. Will this particular assumption, together with the block MDPs, induce some additional structure on the block MDP, or like constrain block MDPs further, or not? Like, do we get all block MDPs with this KD decision trees with this logarithmic depths? If you take those, then is it true or not automatically that this assumption is going to be satisfied?
Which assumption would be satisfied? Oh, the norm boundedness assumption?
Yeah.
Yes.
It will be satisfied?
Yes, it will be satisfied.
And how is that happening? Can you elaborate on that?
Oh, yeah. So basically the way that you show block MDPs or sparse linear MDPs is okay, the way you show decision tree block MDPs or sparse linear MDPs is what you're going to do is if you look at a decision tree,
the paths, like you take the paths and those are the features, sort of, right?
Exactly. Like each path is kind of like a log k wise conjunction. And so your feature vector is going to be the set of all possible log k length conjunctions.
Yeah.
And basically, the property that you have is that the feature. Okay, so basically, all the coefficients are going to be bounded, and you obviously only have k of them, and basically the fact that the probability sum to 1 is going to ensure that the sum of the all the coefficients are also non-negative. So the sum of all the values of mu of s prime is going to be a polynomial in the sparsity here, which is k.
Oh, wait. Okay, right. Yeah. Okay, so the sparsity inherited from the number of latent states. That's the sparsity parameter. Okay, got it. Yeah.
Yeah, so like basically each latent state is going to correspond to one
Right.
non-zero entry of
Right,
the two vectors, and that's why the sparsity is like k.
Right. You go to one of the latent states, and like, I mean, yeah, that's
yeah, and then the fact that you go to one of them means that like the sum over all of the latent states of these coordinates is bounded, and everything's non-negative. So
right.
boundedness and like their values is obviously boundedness in the absolute values.
Got it. Okay.
But yeah, this is a very good point. Like, I think the fact that it's bounded here is maybe good evidence that like this is maybe a somewhat reasonable assumption.
Yeah, not completely outrageous.
Yeah, but we also know that in order to get efficient algorithms, you actually need this norm boundedness assumption. So
Didn't we just like, okay, for linear MDPs?
For sparse linear MDPs, not for
sparse. Okay. So for sparse linear MDPs, you have a computational lower bound that says that if you didn't have that, just remove that assumption, everything else is the same. Then what type of lower bound do you get in this case?
Basically, like if you could, it's essentially kind of reduction to sparse linear regression. So what we know is that if you could solve this, then you could solve some task in sparse linear regression, which is under the absence of a norm bound, which is it's not known how to do that, and it's not believed to be possible.
Oh, okay. All right. Yasir? Yasir has some question. Yasir Yedra? I don't know. I'm not sure I'm saying your name correctly. If you want to unmute yourself, do it.
Hi, do you hear me?
Yes, we do.
Okay, perfect. Thanks for the presentation, Noah. I had the question about the poly dependence on A. So in the work on linear MDPs by Jin et al., there is absolutely no dependence on A. It's just the dependence on the dimension. So I was wondering in this case, for k-sparse linear MDPs, why do you get a dependence on A? Is this like a fundamental issue that has to do with the problem setting, or is this due to the algorithm construction?
Yeah, this is a fundamental issue. So there's a lower bound that shows that you can't get dependence better. You need at least linear dependence on A. This even occurs for like sparse, linear bandits. Basically, like just the standard multi-arm bandit problem can be basically a lower bound for the standard multi-arm bandit problem, which shows that you need like A samples. Can be phrased as a too sparse linear bandit problem.
Okay.
And so there, the sparsity is constant and A is not. So you need dependence.
Okay.
Only for the computation or also in the sample complexity?
No, also sample complexity. They're like this is a statistical issue.
I see. Okay.
So if A is getting larger than D, you're kind of back to the non-sparse setting.
Yep. Yes, you should think of A as being like scaling with the sparsity parameter.
Okay.
And I have another question. Can you perhaps elaborate on this restricted isoperimetry condition that you avoid here? I mean,
yeah.
I didn't really get where exactly this was not needed.
Oh, okay. So I guess some of these prior works on sparse reinforcement learning, what they're doing in some sense is they're basically performing parameter recovery in the sense that they're learning the optimal value function, kind of in a norm sense. And in order to ensure that you can do this in general, you need data that's well conditioned. You basically need data that kind of points in all possible directions.
Yeah.
And go on, sorry.
So basically, if you were to do prediction for linear regression with sparsity, then you wouldn't need that assumption. Would that be correct? Yeah.
That's right. Yes. In order to perform the
Okay.
prediction task, you don't need this.
Okay, I
And
see.
yeah, I guess our algorithm is, making do with only kind of an oracle that does the prediction task in some sense.
Yeah. Okay, thanks.
Yep.
I have a related question, which is that if we simplify these for contextual linear bandits, what is the type of result that we get? Like what is exactly going on there?
So there's kind of a trivial way of doing this, at least for like the stochastic setting, which is just take a uniformly random action. You get a bunch of data, like there's some x drawn from some distribution. You get a bunch of XA samples where A is uniform. Just do the lasso on those and output that gives you some kind of linear coefficient vector. And then you just output the greedy policy.
Is it somehow an underlying assumption that this will give you sufficiently rich data?
So the main, like the kind of, I guess the main thing that makes this work is that the suboptimality of the value of this policy can be related to the prediction error of the corresponding sparse linear regression task. So even if there's like some directions which are not not covered very much by the data distribution, that doesn't contribute much to our policy suboptimality. So I guess is that what you're asking when you say there's no assumption?
Yeah.
Yeah, so I guess this is kind of like, maybe it gives some intuition as to like why this problem is possible in the first place. Because, at least this is essentially the H equals 1 case for RL. At least in that case, we don't need any exploration assumption. We can just kind of make do by solving the prediction task for sparse regression.
Okay.